This is my take two on this. Whoops. Basically today, guys, we are learning about nuclear decay, the warm up, what particles are in the nucleus of an atom. So the center part is made up of two types of particles. We got positively charged particles, which would be called protons. They're positive. And then kind of like a glue in the center, that would be neutrons. They're neutral. The electrons flying around the outside, they are negative. So these neutrons kind of like block or like kind of hold the atom together, because without them, the protons would be attracted to the electrons and it would just be all crazy in that. All right, so our objectives today is just describe, compare, and write the equations for different types of nuclear reactions. So talking about radioactivity and radioactive decay, nuclear reactions can produce high energy electromagnetic radiation, or gamma rays. Nuclear reactions can produce particles of radiation. So anytime, it's basically like when a nucleus is breaking down or energy is coming from the nucleus, that's radioactive decay. And that's when you hear of radioactivity. They are caused by unstable isotopes. So too many or too few neutrons can make a nucleus unstable. Small atoms have about a 1-to-1 ratio of neutrons and protons. Larger atoms have about a 1.5 to 1 ratio of neutrons to protons. So there's always going to be a little bit more when we were doing the mass numbers. That's why there was like a higher amount when we got to the bigger elements. Isotopes with unstable nuclei are radioactive. They release radiation, which is an energy. They can decay and break down, or they can form a new element that's called transmutation. So here's some isotopes of hydrogen. Hydrogen has 3. Protium has 1 proton, 1 electron. Deuterium, I can never say that, 1 proton, 1 neutron. Tritium, 1 proton, 2 neutrons. So there's 4 types of radioactive decay. When things are breaking down, we're going to talk about each of those. So an alpha particle is basically a decay of a helium nucleus. 2 protons and 2 neutrons leave the nucleus. They decrease the atomic number by 2. They decrease the mass number by 4. This is the symbol. That's like that little, it looks like an A in cursive. That's an alpha particle. The mass number would be up here. That's 4. And the atomic number decreases by 2. They're highly ionizing, which means they can gain or lose electrons, and they can be stopped by skin or clothing or like a sheet of paper. So here's an example of an alpha particle, alpha decay of radon-221. Radon on the periodic table, or 221, its atomic number is 86 and its mass number is 221. If an alpha particle decays out of that, think of these equations like the arrows and equal signs. So whatever's on this side, like 86 and 221, you have to have the same on this side. So we said the mass number decreases by 4. So 217 plus 4 is 221. Think of this as an equal sign. And then the atomic number decreases by 2. 84 plus 2 is 86. And you look on the periodic table to figure out what element that is. 84 is right there, it's polonium. And it symbols PO, P, capital P, lowercase o. If you have a beta particle decay, it's basically a high energy electron leaving. It increases the atomic number by 1. It does not change the mass number. And it's highly ionizing, and it's stopped by 1 centimeter of flesh or thin aluminum foil. So this is the symbol of it. Again, it decreases, or it increases the atomic number by 1. And this means it's ionizing. So here's the beta decay of radon. And again, you guys can push pause if I'm going too fast. So here's beta decay. Remember, it doesn't change anything about the mass number, the atomic number. This is going to be 87 because 87 minus 1 is 86. Remember, think of that arrow as an equal sign. 87 is over there, it's francium, and its symbol is FR. Gamma rays is what the Hulk got hit with. It's a type of electromagnetic radiation. It's energy only. This symbol looks like this Y type thing that's called gamma in Greece. It does not change the atomic number. It does not change the mass number. It is highly ionizing, and it's stopped by inches of lead or feet of concrete. So it's just basically energy leaving the nucleus. So these ones are kind of easy because everything's the same. You just put, the mass number stays the same. The atomic number stays the same. This is still tectinium. It's just, it released energy or gamma ray and it hit the Hulk. All right, shielding, you have alpha particles. They can be stopped by a piece of paper. Beta rays can be stopped by a piece of plastic, and gamma rays, concrete, steel, or lead. Positron is something different too. This is almost like antimatter. It's the same mass as an electron. It has +1 charge instead. So it's really small. It's about the size of an electron, but instead of being negative, it's positive. It decreases the atomic number by 1. It does not change the mass number, and it's quickly annihilated when contacting an electron. So that's what a positron looks like. Here's positron emission from polonium. So again, it releases antimatter. The mass number stays the same. The atomic number decreases by 1 because 83 plus 1 is 84. 83 is bismuth, Bi. All right, decay of unstable nucleus. The nucleus becomes more stable. Often transmutation occurs. You saw like we were starting with one element and it changed into a different one. The nucleus decays. And we're going to talk about nuclear bombardment when you shoot a nucleus with another atom and it can fuse together and cause it basically it changed into a different element. So to do nuclear bombardment, you need a particle accelerator, neutrons, protons, alpha particles, other small atoms. You shoot them together, accelerate them so they collide. They move fast enough that they could collide. One of the particle accelerators that we know of, it's in CERN, and this big circle marks the location. It's all underground. It's about 100 meters down, but they accelerate the particles and then they'll shoot them at each other and they do experiments that way. So particles join the nucleus and makes new atoms. New atoms often decay radioactively. So these transuranium elements, that's what that nuclear accelerator makes. They shoot stuff at uranium and they make new elements. So when they talk about man-made elements, and there's waste, but they do not occur naturally, like most of the stuff on the bottom right here. So if you had a nitrogen-14 atom and you bombarded it with an alpha particle, one product is a proton. What's the other product? So to do these, you have nitrogen-14, it's atomic number 7. You shoot an helium product at it. It releases a proton. So if it releases one proton, that's a hydrogen. And then you have to get this side equal to 9. And you have to get this side equal to 18. So that would be 17. That would be 8. You created oxygen 17. A californium-249 atom is bombarded by a carbon-12 atom. 2 nuclei combine, but 4 neutrons are emitted. What heavy isotope is produced? So here you're shooting carbon-12 at californium. 4 neutrons are admitted. Remember, this side, you have to equal 104, and this side has to equal up to the mass numbers. So also, guys, this 4 carries, so 4 plus, 257. This side has to be 104, like I said. 104 is Rutherfordian. Rutherford. The plutonium 239 isotope is bombarded with 2 neutrons. One product is americium 241. What's the other product? So here you shoot a neutron at it, 2 of them. Remember, this side has to equal up to the other side. So, 239 plus 2 is 241. This side has to equal that. So basically, a beta particle was the other product. The alpha decay of radon 221. Go back. This one, it wasn't finished. So remember, this side has to equal up, so that's 84. And then 84 is polonium. Okay, so that's the end of that. We're gonna practice those tomorrow. And I can't shut off my record. Yay. So we'll work on those and, oh.